The topic for today is electric fields. In Physics 1, the concept of gravitational force and gravitational fields were discussed. Now we're going to talk about the electric field as the agent of the electrostatic force. Now, like the gravitational force, the electrostatic force was at one time considered an action at a distance, which means that the two objects that are exerting forces upon one another are not actually in contact. The action is happening when these objects are separated. This works for gravitation. It also works for electrostatics. And so it seems a bit mysterious as to how one object would exert a force on the other. Michael Faraday was the one who coined the notion of a field. What it means in this case is that if I have a point charge in space, let's call it Q, this charge will create an electric field such that if I put another charge in space, some test charge, Q sub t, the force on that test charge, Q on Qt, would be equal to 1 over 4 pi epsilon naught Q times Qt divided by the distance between. So say the distance between equals r. And what Faraday said is that this Q was providing a field in space such that Qt would experience a force due to that field. Now, one might say, well, I'm not so sure that's very satisfactory either. What comprises this electric field? And oddly enough, the answer to that question is not only beyond this course, it's also beyond this course. We don't teach the real truth about how electric forces and fields operate until we take a course in quantum electrodynamics. I'll give you a hint as to what the answer is now, even though it's a long way away before you actually study all of the principles behind it. The electric field is caused, or I should say the electrostatic interaction between these two charges is caused by the fact that they exchange photons or particles of light. And that's what causes the interaction. That's why the field is present. Now, we won't talk about that in this class, and as I say, you won't even talk about that in classical electrodynamics in graduate school. It's beyond that. But that's the real answer for those who feel that, okay, you've just transferred the spooky action at a distance from a force to a field, and you haven't made me any more satisfied. We gave you kind of a quick answer, although you're many, many semesters away from actually studying it. Nonetheless, we can get some mileage, some really good mileage, out of studying electric fields. So we can say then that charge Q sets up a field around it such that the electric field, when I multiply by charge Q, will result in a force. That is to say, the Coulomb force. So this electric field is an entity that has units of newtons per Coulomb. And in the case of a point charge, it's very simply written as, for example, using the positive test charge. In the previous example, I can write the force on that charge as the size of the test charge times the electric field due to charge Q, which tells me the electric field due to charge Q must be Q over 4 pi epsilon naught r squared. Notice the difference between this expression and the force expression. It's a factor of Q that's removed. So the electric field that's caused by a point charge Q, is equal to Q over 4 pi epsilon naught r squared. It also has a 1 over r squared relationship. It's also a vector quantity. And the electric field vector, by convention, if I have a positive charge, positive point charge, the electric field lines emanate radially all directions outwards. This is by convention. So they emanate radially from a positive charge. Conversely, if I have a negative charge, the electric field lines emanate in towards the charge from a radial direction. Moreover, the stronger the charge, the larger the charge, the more dense the field lines. So in this case, if this is a big positive charge, and that's a smaller positive charge, this one will have many, many more field lines emanating from it. So what, kind of like the Cheshire Cat, even if there isn't a test charge in space, if I have a point charge in space, it's going to create an electric field that will be there even if the test charge no longer is there or was never there. We can calculate electric fields in the same way that we calculate electric forces. And we can show it again, keeping in mind the superposition principle and the vector nature of the electric field. Let's do a good example of this, and we'll illustrate more of what we mean as we go. Suppose I have the following configuration. Here's the origin, and I have 3 point charges. I have one that's 5 meters in the negative x direction, and we'll call that Q2, and it has a charge of 2 microcoulombs. I have another charge located at minus 1 microcoulomb at a distance of positive 3.5 meters. Okay, so this isn't drawn to scale. Then I have another charge, a third charge, located at, and we'll call that Q3, and that's equal to minus 1.5 microcoulombs. And that's located at a distance of 4 meters up the y-axis. Okay? What I'd like to do is to calculate the electric field due to those 3 point charges at the origin, taking advantage of the vector nature of electric fields. Here's the way to do it. I'm going to find the magnitude of each electric field, the field due to each of those charges. I'm going to break them into components, and then I'm going to combine the x components, combine the y components to get the magnitude and the direction of the total electric field. So immediately, I can say E1, we'll just get magnitudes. We're not going to worry about the signs of the charges just yet. Magnitude of E1 is just going to be 1 over 4 pi epsilon naught times Q1 divided by, in this we said is Q1 divided by 3.5 meters, we'll square that. And by the way, the only component of E1 is going to be in the x direction. There is no y component because Q1 lies along the x-axis, so I can write E1, and I can call that E1x, just as simply. And the magnitude would be, if I put in my numbers, I'm going to get 730 newtons per coulomb. Again, not worrying about direction, I'm going to look at, in this case, Q2 is all in the x direction as well, so I'm going to say E2x is 1 over 4 pi epsilon naught Q2 divided by, in this case, 5 meters. I'm going to square that, and that's going to give me 720 newtons per coulomb. And then I'm going to calculate the magnitude of E3. That's all in the y direction, by the way. There is no x component with respect to the origin. Remember, everything is with respect to the origin in this problem. So it's E3y, 1 over 4 pi epsilon naught. That will be Q3 divided by the distance is 4, Q3, 4 meters squared. And that has a magnitude of 840 newtons per coulomb. Let's look at the directions now. By convention, Q1 is a negative charge, therefore the field line from the origin will point in this direction into Q1. It's a negative charge, so the field lines point into the charge, so it's going in the positive x direction. By the same token, Q2 is also moving in the positive x direction because it's a positive charge and all field lines emanate in a direction radially outward from the positive charge. So both Q1 and Q2 are going in the positive x direction. Therefore, Ex I can write as 7, so that's going to be 1450 newtons per coulomb total. E3y, on the other hand, is a negative charge. That is a field that's moving into the charge, so it's moving in the positive y direction. So Ey, because Q3 is the only charge that's creating a field that has a y component, is equal to 840 newtons per coulomb. When I want to find the magnitude of the total field, then I can say that the magnitude of E is equal to the square root of Ex squared plus Ey squared, and that's going to be equal to, if I put my numbers in there, I'm going to get that it will give me 1700 newtons per coulomb, and because this is a vector quantity, every time you calculate an electric field or electric force, you had better incorporate a direction. The direction, and we'll call it phi, is equal to the arctan, the angle whose tangent is Ey over Ex. Turns out that phi, if I put in my numbers, that would be 840 over 1450. Arctan of that gives me 30 degrees with respect to the x-axis. Generally, we always do it with respect to the x-axis. So that's how I would calculate the electric field due to 3-point charges. We've got a couple of interesting special cases of electric fields. Let's do one for the dipole. Suppose I have two charges, plus Q and minus Q, and suppose they're equidistant from the origin, some distance A in each case from the origin, and I want to find the electric field due to these point charges at point P. And suppose we'll call that distance Y, we'll call this distance R, and this distance R. They're the same distance, they're the same size charge, except one's positive, one's negative. I want to find the field at this point. Call that angle theta, call that angle theta. Notice, we can make this problem simpler by symmetry. If I look at the field at this point due to this positive charge, it's pointing up in this direction, right? Emanates away from the positive charge. The field due to this negative charge, by convention, emanates towards the negative charge. If I look at the components, the x component of this field is going in this direction. The x component of this field is also going in this direction. But the y components will cancel each other out. So that y component due to this charge will be canceled out by the y component due to this charge. So all I have to worry about is the fact that I have reinforcement in the x direction. So my Ex component is going to be twice the Ex for each charge. Makes it much simpler, and I can do the following. I can say then that the only components that survive are the EX components. I can say then that that's going to be 2 times in the E, let's call it the positive, times the cosine of theta, which will give me 2 times Q over 4 pi epsilon naught R squared times cosine theta. I can use some trigonometry here. I know that R squared is equal to A squared plus Y squared. I also know that cosine theta is equal to, in this case, it will be the adjacent A over R, which I can write as A over square root A squared plus Y squared. Put that all together, and so the electric field due to one of those charges can be written as 1 over 4 pi epsilon naught Q times A divided by 4 pi epsilon naught Y squared, sorry, A squared plus Y squared to the 3 halves. Since I have 2 of them, of course, the total field then is going to be twice 2QA over 4 pi epsilon naught, not twice, 4 pi epsilon naught A squared plus Y squared to the 3 halves. So this term, this 2QA term, is very consistent with that of a dipole. Interesting follow-up on this. Suppose we have a case where Y is much, much greater than A. So suppose we're at a very far distance from the dipole, such that the distance between the charges is really small compared to the distance away from the dipole. If that's the case, we can neglect the A squared in the denominator. We can't neglect it in the numerator because we're multiplying by that. So in this case, E is approximately 2QA divided by 4 pi epsilon naught, and that's Y squared to the 3 halves, or just Y cubed. This is very, very characteristic of a dipole field. It goes as 1 over the distance cubed, something nice to remember. This will occur over and over in physics as you study more electrodynamics. The quantity, by the way, QA, is often called a dipole moment. And you've probably heard of those when you study chemistry, like the water dipole and so on. Dipole moment is the charge times the distance between the charges. Sometimes we give it the letter P. Well, we've talked about electric field lines. I'd like to talk a little bit more about them, again by convention. So, for example, if I have an electric dipole, so I have a plus charge and a minus charge, what's going to happen? All of the field lines emanate from the positive and go to the negative. I'm going to have a field lines that look like this. So going from the positive to the negative charge. Kind of looks like a field of a bar magnet. Don't want to give too much away. That's much later in the course. Suppose I have a parallel plate capacitor. So I have one plate that's all positive charges and one plate that's all negative charges. Let's say we'll use those a lot later on. Field lines emanate nice and parallel from the positive plate to the negative plate. So that's a nice configuration to look at. The other configuration that might be interesting is suppose I have two positive charges, two equal positive charges, something like this. In that case, we're going to see that you're going to have field lines where they're in between them, in between the charges, there's going to be no field. Say the charges are equal. There's a space in between where the field is going to be 0 because the lines are going to are going to be equal and opposite. So those are some nice examples of how we operate with point charges. In a course that is able to use calculus the way ours is, it becomes interesting then to look at the electric field lines of continuous charge distributions. I'm going to talk a little bit about that in this segment, and I'm going to leave the examples for the next segment. Let's talk about continuous electric field due to a continuous charge distribution. Suppose you have instead of just point charges, suppose we have a charged blob, like so. And I want to find the electric field at some point P in the distance due to this charged blob. Well, one might say, let's just divide the blob up into a bunch of bloblets, and each bloblet being a point charge, and let's add up the field due to every one of those point charges. In other words, I can divide this up. Suppose that the total charge of this guy is big Q. I can break this into little q's, maybe little pieces of plus Q and so on. Or maybe we'll call these delta Q's. That might be better, delta Q, delta Q. And it would be fair to say the electric field due to one of those little deltas, I'll call that delta E, would be 1 over 4 pi epsilon naught delta Q over r squared, and of course the r direction. That would be for one little charge element. And we'd say that by superposition, I should be able to add up all of those charges and get the total electric field. That would be true. Operationally, that would be a disaster. But of course, calculus allows us to do the following, and you've seen this trick before. Let us do this. I can say E, I'm just going to take the limit as delta Q approaches 0 of this configuration, 1 over 4 pi epsilon naught delta Q over r squared, r direction. And of course, what this tells me is as delta Q approaches 0, I can now write this as an integral, 1 over 4 pi epsilon naught integral dq over r squared in the r direction. This is, in principle, the way you would solve an electric field problem for a continuous charge distribution. This is only going to work well, though, if we have nice symmetrical configurations. There are some other things that will help us, though, as we do this. Typically, we don't like to work with elements of charge dq. There's only one example where we do. We'll do that next time. Typically, though, we would rather do integrals with respect to space. And so we have the following identities to make. I can define rho as a charge density, a charge per volume. I can write sigma as a charge per area. That's what we call a surface charge density. And I can write mu as a linear charge density, lambda linear charge density, Q divided by a length, or Q over X. And by that token, by the same token, I can write dq as rho dV. I can write dq as sigma dA, and I can write dq as lambda dx, as the geometry of the problem calls for it. We'll do some wonderful examples of continuous charge distributions next time. Thank you.